Hello and welcome to Advent of Code, day 23. Missed yesterday on time, but was able to solve it pretty quickly once I took a look at it. Yeah, now just waiting for the next problem. It's a Friday night. I'm not sure what that means for how difficult or time consuming the problem might be, but I'm excited anyway. All right. Experimental coprocessor. All right. Set sub that tablet. Okay. Uh-huh. All right. So this was, okay, I remember this. General functionality, some of the instructions are different. 8 registers, some kind of debug mode. If you run the program, how many times is the mul instruction invoked? All right. So let's talk about reading this here. Okay. Okay. So we have set, sub, mul, and jump non-zero. So let me just see if quickly I can find. Okay, so we got a little something here. Let's just copy this in. So I think I can take out this receive, the mod. Actually, I especially don't have to take these out. So okay, so set xy sets the value. All right, let's take a look. Okay, so set is always okay. So I think I need this read reg. Definition here too. Yep. Okay. All right, so we have our set. So we have jg0. This is actually jn0. So it's a not zero value. Okay, so we'll just say not equals here. Mul multiplying the value by, okay, only the instructions listed above are used. And do we have sub for subtract? Looks like no. So let's maybe just take, let's just take add and change it. Okay. Blocks. Why does it want? Ah, right. Yeah, okay, so let's just take this part out. Sends. Okay, don't need this either. Okay, step. Now, the question is how many times is mul set? Okay, so let's just have this be muls here. And actually, here, let's just change this last thing to muls. Or actually, here, we'll leave this to be the same. We'll just use this as, so, like this. Okay, pretty sloppy here. Okay, so then an ID that doesn't matter. The program counter starts at 0. Registers are an empty collection. Sends doesn't matter. So I'll just say 0 there. Rescue. Okay. So something like this is the starting state. And I think we already have, do we have reduced in here? Yep. Okay, but then we definitely want to make sure that we emit this thing. All right. Okay, define this, and then reduce step, starting here, range, I don't know, 100,000. Something like this. Okay, let's just turn this off. All right, so we have an answer. Let's give it a try. Good answer, Mike, 79. Okay. Next part, debug mode switch is wired directly. Now register A starts at 1. Okay. 1, there, did it. Whoever wrote the program didn't choose an efficient implementation. Is to determine the final value left in the register H once the program completes. If it had that, it wouldn't even need to run the program. If the program were to run to completion, what value would be left in register H? Okay. So it seems like, okay, so looks like H starts at 0, and then there's some sense in which, okay, there's some kind of looping going on here. Well, let's do this. Let's run the program and just examine it at various points here. Too many, right, okay, let's do this. Because, yeah, I definitely believe them when they say that this is just going to take forever to run. But, so let's talk about, I guess, the regs, so regs is going to be like the fourth thing in here. Okay. So looking at this, it seems like it hasn't even gotten to H yet. So my guess is that maybe this value, so G is changing a lot, E is going up. Let's see, let's take a look at the program counter. So where's the program counter spending its time? 17, 16, 11. Okay, 11, it's spending its time in lines 11 to 18. So let's take a look here. So this is actually line 11 here. And then, so it looks like jump non-zero G. Okay, so it like needs to wait for, so okay. Jumps 2, so it goes up here. Subtract 1 from E. Set G to be E, set G to be this, and then here go back 8. So 8 like this. So basically, at a certain point, G is got to be 0. And then we're going to move on to the rest of the program. And okay, so let's see, 13 go back up. Geez. Okay. Sub H -1 set sub. Yes, okay, so at some point it's going to maybe go here. Okay. Aha. All right, I think I'm seeing this. Jump non-zero G, this. Jump non-zero 1 negative. Huh. So how does this actually exit? Checking that this program in fact is still running. Yeah. Yep. Okay. All right, so how does this program actually exit here? So the last thing is, oh, okay, jump non-zero 1 3. Okay, that means if you get to line 30, then you win. All right. So that means that at a certain point, G is going to have been 0. All right. So that means that G is basically doing a check for, so you just subtract. So like a check for G equals C here. So in other words, this is a check for B equals C. Okay. Jump non-zero F. So basically, if we get to this point and if F is 0, then we're subtracting 1 from H. All right. Let's look at the registers again. So F isn't changing a lot. Hmm. Hmm. Huh. E equals 2, G equals D, G equals G times E, G equals G minus B. If G is not equal to 0, then actually if G equals 0, then what this is saying is F equals 0, like this. Okay. Sub E negative 1, so E plus plus. Set G equals E. G equals G minus B. Jump non-zero, G 8. Okay. So leave this here. E plus plus equals D. G equals G minus B. Okay, so this idiom keeps repeating itself in the program, which is like you're jumping back until the point. You're like making sure that G is equal to something else. So in this case, or you even, no, this is sort of saying like B is equal to E. This is saying B is equal to D. And then this is saying B is equal to C. Interesting. And all right. So it seems like D, E, and G are getting like all the work that's happening to them. Okay, interesting. Um, hmm. Okay. All right, so this all makes sense. Let's start looking at these jumps here. All right, this jump is accounted for. This jump goes back 8. So, and then this jump goes up 13. All right. This goes to line 12. And this goes to line 11. Or some other J and Z's. Okay, this one is just saying if f equals 0, then h minus or h plus plus. So it's kind of like how often does it get to this point? Okay. Jumping on 0. 1, 3. Okay, so this is the exit. Okay. So this is basically saying if G is 0, then exit. Right? Otherwise, we're jumping up to 9 here. Okay, so I think I kind of understand the program a little bit. So let's call this point in the program foo. Maybe I would do it this way. Foo program bar and this point of the program Baz. Okay. Let me open up another terminal here. Try to translate this into. All right. So we have foo here given by f equals 1, d equals 2, r g equals d, g equals g times a minus b if d. Okay. Okay, g equals e, g equals e minus e. If, so I think we can just say, like, if this is the same thing, then go to bar. Okay, then we have Baz up here. All right, D++. Okay. G equals D, G equals G minus B. If B is equal to D. On 0, go to Baz. So this is, so if you set this to be this, and then you do a jump on non-0, that would be this actually. Okay, then out here we have if okay. then okay, if B is not C, then go to foo here. Okay. So basically, it seems like the program needs to get to a point when B, E, D, and C are all the same. Are all the same value. And yeah, it seems like, so I'm not sure what the function of F in this program is. Let's take a look. It gets set here. It gets set. Oh, I see. There's a check. Okay. So it gets set up here. And then basically, so it's possibly going to be set down here. Okay. So let's see. What is the mechanism by which B, C, D, and E change their values? So E is incremented here. B is incremented here. So we're still looking for B and D. Okay, D, set D to 2. D plus plus. Okay, so there's D. So B, C, D, and E are the ones that we care about. Okay, where's B changed? Okay. All right, I'm not seeing B. Here we go. B equals B plus 17. Okay, so so here's the exit check. It's not equal to C. So it isn't just a go to foo. Also B plus equals 17. This counts for B. All right, and then how does C change? Doesn't. All right. So okay, so we need it to be the case that B is equal to C, and it's going to be increasing by 17 each time, which means that this outer loop is going to happen 1,000 times. So this is gonna go 1,000 times. What impact does that have? This here. Not sure yet. Oh, okay. Actually, the main thing that I care about is how often F is 0. That's going to determine, yeah, okay. So I think these lines get executed 1,000 times. So the question is just how often F is 0. So what are the things where f is being set one way or the other? Set to 1 in this code. Okay, set to 0 here. Okay. I'm gonna go with 1,000 here. Because we need to get to the place where B is equal to C, and that's only going to happen when this code gets executed 1,000 times. Not the right answer. Okay. Well, f is 0. I think I'm just not understanding. Let's see. Oh no, it gets set to 1 here. Okay. All right, so I think the question becomes, how often, when you break out of this, how often is g, set g to d, multiply it by 3, and then subtract. Oh, interesting. Okay. This is basically saying whether it's the case, if it is 0, so if these two things are the same, so this is saying whether d times 3 is equal to b. Okay. And d, it looks like it's just sort of increasing time. So maybe it's like it's just increasing by 1. Do we have a d plus plus? Yeah, we do. All right. So if d is a third of b, then we set f to be this. So I think the question is how many times in those 1,000s, in that 1,000 loops, is d times 3 equal to b? So yeah, based on this, it does seem to be just increasing one at a time. How? So it hasn't. Well, so how is f set to 0 in the first place here? Because when we got here, then I've got a little idea, I think. So that maybe we could change this program to like reduce some of these values. Like maybe we could, like we could possibly just set this, but the thing is that C and B haven't changed at all. So like that's not even going to be enough. All right. Okay, so I think that we can just take these lines out. Okay. Yeah, G is, I'm pretty sure it's just used as a temporary variable here. So I'm going to clean this code up a little bit. Similarly here, okay, the structure is starting to fall into place. Okay, so basically, okay, so F gets set to 1, D to 2, E up here, and then we can just say B equals 10, 6, 500, C equals 100, like this. It's what it's been just since the program started running. Okay. Situation, do this, okay. And then finally just return. All right. So let's talk about, I guess, this block here. So increment E up to the point where it's equal to E, and until that point, okay, hang on a sec. Jump non-zero. Set G to be E, then subtract this. And if the result is not 0, then jump up. Okay, so this actually should be like this. Okay. Okay, this makes a lot more sense. So okay, so this is basically incrementing E one at a time until it's equal to B. And along the way, it's just doing this check here. Okay, and then this outer one, this is incrementing D until it's equal to B. And then it goes back up here, it resets E to this thing. Okay. Huh. So yeah, I wonder if I could just set B and C to be smaller values that nevertheless had 1,000 runs between them. I think that will work. So I think I gotta like change, I think I want to change the actual program. So basically, so okay, these need to be okay, so this is what the effect of going into debug mode is. Okay. So this is the effect. So I'm going to turn debug mode off because these are just basically setting B and C. So, or actually, how about I do really don't want to. I really don't want to delete too many lines here. Set b to 65. So set these both values to 65. All right. So that explains why the program ran quickly. Okay, why don't I just do something based on the program counter? So I'll say if the program counter is at 7, um, then instead of doing this thing, I want to just return id the same program, increment the program counter, and then assoc in regs. So the way we have it here, we're going to set B to be 65. And C to be the difference here. So add to 65 the difference between this and this. Regs. Leave this the same. Leave this all the same. And then otherwise, do all this stuff. All right. You can just stop. All right. Let's redefine this. Try running it. Okay, this didn't work. Does the program counter not get to B7? Should for right here. Oh, okay. This back in. On this again. All right. Okay. Okay, cool. This is looking a lot better. All right. So yeah, we're waiting for the value B to reach the value C. So looks like we're about 1/30th of the way there right now. So not super speedy, but I don't think that the program is going to get any slower as it continues on. Yeah, I wonder if we can maybe figure out what is going on with H to try to like estimate this. I don't know. I'm also not sure if it is just maybe going slower right now. We could, yeah. Stare at the program a little bit more. I guess there's this part, which is, this part's a little bit worrying. Because we are changing the value for B. Okay, so here's a situation where F was incremented. Still going pretty slow. Yeah. I don't know if this is going to produce the right answer. Um, hmm. And it's going pretty slowly. It's only 5% done. Okay, so let's look at this some more here. Um, hmm. So hmm. Okay, looks like I copied this part wrong. So set G to D, multiply D by E, and then check whether that's equal to B. So that's asking this here. So this might be an easier question to answer. So this is asking how many times, whether it's the case that if we have, so we have the values D and E, we're asking how many times is it the case that as we're going up this thing, that these values multiply together to produce this. So if both of them are going, so if this loop here sets every value of E, then I think the question is how many numbers, I think the question is how many divisors does B have that are like greater than 2? I think it's like something around that. Um, well, so yeah, it's basically take all the different take all the different values for D and then find out if it yeah. Yeah, I think that has something to do with it. And then do it 1,000. No. So what is the point of doing this 1,000 times? So this is okay. So this is kind of like 4D in 2 all the way up to B, 4E in 2 all the way up to B. Does D times E equal B? All right, and then what is the outer loop of all this? Um, like if so, increment H. And then so then the point of this is that we're doing something, we're doing it 1,000 times? I don't understand. It, what else is happening in this outer loop? I think, so this is how I interpret it. It is doing something, so it should be doing it exactly 1,000 times. So I guess understand. Oh, okay. I think I got it. I think I got it. How many numbers in this range are prime? I'm pretty sure. So, okay, do I have a prime definition? In fact, I do. Okay. So let's take this. Okay, and then range of numbers starting here, going up to this one, and going up by 17 at a time. Filter, or I guess remove the ones that are prime. Count. File wow. Okay. 916. Yeah. Yeah, that kind of seems right. So there's going to be 1,000 things in here. I guess I just need to make sure that. So I think when B equals C, that we are doing these things here. So we start by checking this one, and then I think we end by checking the other one. Because pump it up to this level, and then yeah. So maybe, so what happens if we did this? Yes, this would include that last one. 917. Right answer, rank 79. Cool. Very cool. Yeah. That was an awesome problem. That was probably the funnest one that I've ever done of these. Yeah. Yeah, hats off to Topaz. So yeah, let's talk about this problem. So step one is basically working with this processor from the previous problem. Now I thought that I brought the code in from the other from that other day. I thought I brought that code in pretty quickly, but it seems like other folks did as well, because if we look at the day here, yeah. So rank, interesting, rank 79 on both. So yeah, it's just about 4 minutes, 4.5 minutes. The first, yeah, 3.5. sorry, 1.5 minutes to get the first part here. So yeah, pretty straightforward. Just this was like a jump greater than 0, so I had to change that. Set, sub, mul, these are the ones that matter. I ended up just repurposing a state variable. And just to count the number of multiplications, which was the first part of the problem. And then then the second part of the problem was to figure out basically figure out what the program was actually calculating. So yeah, I basically started by like just annotating the program in like pseudocode here with some labels, and then found out that it actually turned out to be something that was pretty structured. So I made a mistake by when I transcribed this as this here. I guess because E and 3 are close on the keyboard, and they kind of look like each other. But so the joke basically is that the outermost loop is checking all values of B. So it's incrementing B by 17 each time, which is what this does. And then it goes to the very, very outermost part of the loop. In the outermost part of the loop, so it sets F here. This F is a flag that is turned off by this checker here. And F is what controls whether this thing is incremented. So basically, the loop is it's basically iterating over 2 variables, D and E, and it's checking to see whether multiplied together they produce B. So the effect is basically for each value of B, which there are 1,001 different values here. For each value of B, it's trying to see if it's the case that there are 2 numbers that between from 2 all the way up to it. There are 2 numbers that you can multiply together to make B. So yeah, so what that is just testing whether the number is prime or not. If a number is prime, then there aren't any numbers that you can check. So my initial guess, noticing that it seemed like H was incremented in the outermost loop, which I knew would run like 1,000 times, which I guess turned out to be incorrect. But my initial guess was 1,000 because I wasn't sure under what conditions this flag F was going to be set. I guess I can stop this program from running here. Anything. So, so the question becomes, how many numbers in this sequence are not prime, composite? So this is, this is just a pretty straightforward definition of the primes in Clojure that I wrote for fun. I'm not even sure I wrote this for Advent of Code, but I had it in my backlog anyway. It's fairly easy to write. You just basically, you have a sequence of primes that you sort of declare lazily, and then you say, all right, if you have a number n, then there's a least non-trivial divisor of it, unless there isn't. The trivial divisor is just being 1 and n. So the way that you find it is you just work through the primes. The least non-trivial divisor of any number is a prime number. So just grab these while they're no greater than the square, where the no greater than the square root of the number, essentially. Find one where the remainder is 0, and then just give the first one a number is prime if it doesn't have a non-trivial divisor. And then the definition of the primes themselves are start with 2, and then filter on prime, just all the odd numbers starting with 3. So yeah, it's a nice mutually recursive definition. You can see here that these are the 100 primes. It's fine for small numbers of primes, but in any case, so I use range here to produce all of the numbers from here to here, inclusive, an inclusive range, which is why this is 01. And then, yeah, just remove the primes and then count them up in the answer. So, yeah, very fun problem. Yeah, let's take a look at personal stats. Did I get, all right, almost 500 points with 2 days left. So looking at the leaderboard, this means that it's not completely out of reach, but also probably going to have to get lucky or I don't know, have a good performance. So yeah, so I'm gonna leave it here. Maybe look at our advent calendar as it fills up and in the way that it does. Lovely, just lovely. Great. Okay, well then, yeah, like I said, I'll call it here and be back on tomorrow. Thanks for watching.